Hey, Honors Math 4 kids, we are going to be going through a little bit of 11.1 here. We'll see how much we can get through in this first video before we need to pick up on a second video. We're going to start with average velocity to introduce how we're going to attack instantaneous velocity here in a second. Average velocity is finding the change in position over the change in time. Obviously, this is related to slope. If we talk about delta S over delta T, it sounds a lot like how we found slope, delta Y over delta X. So if you are using position as your dependent variable on your Y-axis and time is your independent variable, then really we are finding the slope. Have a pretty straightforward example here. Car travels 120 miles in 2.5 hours. Its average velocity over the entire time period we're going to find by taking delta S over delta T. So our change in position would be 120 miles. And that's because really our ending position was 120 miles and our starting position was 0. So I'm going to actually write it like that. Our finishing time was 2.5 hours. So I'm going to put 2.5 here. So basically at 2.5 hours we were 120 miles away. So it's like saying that our second point was 2.5 comma 120. And our first point is 0, 0, because we started at 0 time and we started at 0 at a 0 position. Obviously this just simplifies to 120 over 2.5, but this idea kind of will tie us into slope. So the 120 over 2.5 gives us 48, and our position was in miles and our time was in hours. So our average velocity was 48 miles per hour over that trip. But what's a little bit more interesting thing to look at is what your instantaneous velocity would be at any point in time. So we're going to first come down here. I'm going to skip through this first example here and come all the way down here because this is kind of rehashing through what we just did in example 1 at the average rate of change. If we have a function f of x, the average rate of change of y with respect to x on some interval a to b. So here's our interval a to b, and this is just some function that represents, in the case that we had before, let's say we have position and time, and we're going to look for the average rate of change. So in that case it was velocity, but this could be any average rate of change depending on what this function is actually representing. But if this is a and this is b, this would be f of a and this would be f of b here. So what we're really finding when we find the average rate of change is the slope of this line from this point to this point. That's called the secant line. The slope of the secant line through those 2 points, a, f of a, b, f of b. So to find the slope of that line, I kind of took over my spot here to write my formula, so I'm going to have to come down here and do it. The slope of that tangent line would be, if we did delta y over delta x, it would be our second y value, f of b minus f of a, all over b minus a. That's how we'd find the slope of that secant line. So if we come back up to example 2 here, what we want to start looking at is instantaneous velocity. All right, so we are given this scenario where a ball rolls down a ramp. The distance that the ball is from the top of the ramp after t seconds is exactly t squared feet. So our function is s equals t squared. Position is time squared. There's a graph of this function over here. Wants to know what the instantaneous velocity is after 3 seconds. So we're talking about instantaneous, not the average velocity. If we wanted to find the average velocity between 0 and 3, let's see, we know at 3 seconds we'd be at 9, 5, 6, 7, 8, 9 because of our function, s equals t squared. So we know that at 3 we have a point here at 9. So if we were finding the average velocity, we'd be finding the slope of this secant line between 0, 0 and the point 3, 9. That's not what we're doing here, though. We want to find the exact velocity just at this point 3 seconds into the ball rolling down the ramp. Obviously, the ball takes on different velocities as it goes down the ramp. Because of the curvature here, we can see that the ball is actually gaining speed as it goes down the ramp. So let's do this. let's start by setting up our change in y over change in x here. If we just did our second y value, which would be 9, minus our first y value, which is, wait, it's also 9, because we're doing it from the same point, over our second x value, 3, over our first x value, which is, you see this doesn't make any sense. First of all, we're taking 0 minus 0 over 0 minus 0. For all sorts of reasons, this doesn't make sense, but the main thing I want to look at is the fact that we're dividing by 0. That can't happen, so we need a better way. What we're going to look at is the interval from 3 to t. Okay, so we could look at some interval from like before I said from 0 to 3. In this case, we're looking from 3 to t, so some other point besides 3. If you want to say it's past 3, you can. From 3 to t, but what we're going to do is we're going to say we want t to actually be 3. Okay, kind of what we did here. So we have from 3 to 3, but that doesn't make any sense. We're going to let t approach 3. But remember how we wrote this in the past. We use limits, and that's why it talks about limits up here. We're going to find the limit. Okay, so this is kind of the start of our problem here with all this mess out of the way. The limit, as this value of t approaches 3, of delta s over delta t, which is going to be t squared. Okay, there's my first x value. Maybe I should put that down here first. Or my second x value is t. And my second y value is going to be from putting t into this function. Well, we see that if we put t in, we get t squared. So that's where this comes from. Our first x value was 3. So we're going to take t minus 3. So you see the difference in x values is down in our denominator, t minus 3. Oops. And the difference in our y values would be these values squared. T squared I already have, minus that value squared, 9. Because y, or our s value, is coming from the function s equals t squared. Okay, we still can't evaluate this limit because I can't put 3 in to this function and evaluate it, because this function, if you remember our rational functions, is not continuous at the point t equals 3. But we have a little fix here. We can factor our numerator, to be t plus 3, t minus 3, over t minus 3. Now, we can cancel those t minus 3's out. So this limit becomes, the limit as t, approaches 3 of t plus 3. Now, it's okay for us to put that 3 in, because it doesn't give us a 0 in the denominator anymore. If we put 3 in, this becomes 6. So we just found that the limit of this function, as we let this point and a second point, which I don't even have drawn here, get closer and closer to one another, so that the distance between them is 0. Basically what we did was we took 2 points like these down here, and we just brought them closer and closer together. It's like we took this b value, and we brought it closer and closer to a until it was a. All right, so we were trying to close this. We were trying to close this gap between these two x values right here, and essentially we're trying to make this gap approach 0. And later on, we're going to call this gap h, which doesn't make a whole lot of sense right now, but bear with me. So what we did was we said, okay, if we let t approach 3, so that basically these are the same value, and these end up becoming the same value, 9 minus 9, but if we simplify, we can evaluate this thing and we get 6. So what this means is that the velocity is 6 feet per second at 3 seconds. Okay, now here's where our connection to the next example comes in. That's actually the slope of the line that is tangent to this curve at that exact point. I don't have a ruler here, but if I were able to draw a nice tangent line in here at that point, guess what? The slope of that tangent line would be 6. Okay, and I got a little blurb over here that says that the slope of the tangent line at t equals 3, or at 3 comma 9, is m equals 6, the same as our instantaneous velocity. Clearly math is awesome. Okay, slope of the tangent line, instantaneous velocity at that point, exact same thing. So when we come down here, it says finding the slope of a tangent line. So now they're getting rid of the they're getting rid of the whole instantaneous velocity idea and just saying we have any graph. This is just s equals t squared. Fortunately, it's the same graph that we had before, so we're kind of used to dealing with this function. S equals t squared, or even y equals x squared. We want to find what the slope of the tangent line is at 1, 1. So if this did represent position and time, we really would be finding the instantaneous velocity. Okay, instead of at 3 seconds, we're finding it now at 1 second. Okay, so basically we're looking for the slope of this line right here. Whatever that slope is. I missed, but that's okay. So we're going to find the limit as t approaches, well, now we want our x value to approach 1. Okay, because we're going to evaluate this at 1. So one of our x values is going to be 1. The other one we want to have it get really close to 1. So we're going to call, oops, let me put the 1 right there. So we're going to have our change in our x values to be t minus 1 down here. So again, we would like this t to become 1 because that would make our denominator 0. In the numerator, we have the same function, s equals t squared. So our y values need to be the x value squared. So our x value here squared to be t squared. Our x value here squared to be 1. So this then can be factored to t plus 1, t minus 1. We're still looking for t to approach 1. And like I said in class today, you want to get out of this problem as soon as you can. As soon as you can put 1 in, do it. We still can't put 1 in because it would give us a 0 down here. But as soon as we do this, we then can put 1 in. And we know that the limit, I'm going to go one more step here. The limit as t approaches 1 of t plus 1, if I put a 1 in now, I get 2. So what that means is the slope of that tangent line is 2. Now I'm going to write it as a slope equals 2 because that's what they asked us to do, is to find the slope. All right, again, if they were talking about instantaneous velocity, I would say it was 2 feet per second. But that's the slope of this line here. There's a little picture of that same graph down there. The slope is m equals 2. So we're going to pick up with what a derivative is in a little bit more definition form in the next video.